One of my favorite applications of matrices and vectors is the theory of directed graphs, or digraphs. So what is a directed graph? By definition, a directed graph is a collection of nodes and arrows. So a typical picture of a digraph looks something like this. You can see here we have a bunch of dots that are labeled with V's here. Those are the nodes. And then you'll notice that there are a bunch of arrows pointing between these nodes. These arrows are labeled with A's. Now, for example, this particular digraph has 6 nodes and 7 arrows. Now, why would anyone care about studying a directed graph? Well, directed graphs are often used in models that describe relationships between objects. Here's an example. What you're looking at here is a figure where I have a directed graph on 3 nodes, and the idea is that each of these 3 nodes represents some financial institution. So I have a node here representing Wells Fargo, a node here representing Chase Bank, and a node here representing Citibank. You'll also notice that I have arrows pointing between these financial institutions. Well, perhaps in this model, the arrows are meant to represent transactions between the institutions. So this arrow T1 here points from Wells Fargo to Chase Bank. That arrow would represent a transaction where Wells Fargo sent Chase Bank some money. Over here, maybe I have this arrow T4. T4 points from Chase Bank to Citibank, so that would represent a transaction from Chase to Citi. And you'll also notice that T5, our 5th transaction here, also goes from Chase to Citi. So there's no reason why we can't have 2 different arrows that start and end at the same locations. Now, another area where we could use a directed graph is the internet. If you think about it, what is the internet? In some sense, it can be distilled down to a bunch of web pages and then a bunch of hyperlinks between web pages. So in this example, I'm using a directed graph on 4 nodes to model part of the internet. One of the nodes here represents Wikipedia, another node represents Amazon, another YouTube, and another Netflix. The idea is that these are 3 important web pages and they link to one another. L1 here is my first arrow in this directed graph, and it represents a link that takes you from Wikipedia to Amazon. Here, L7, it represents a link from Netflix to YouTube, so on and so forth. So in this situation, what we're doing is we're modeling hyperlinks between web pages. And social networks are directed graphs. Here you're looking at a picture that is a visualization of the Facebook network, I believe sometime around 2010, so I'm sure the picture is quite different now. But the idea is that if you view every account on Facebook as a node and a giant directed graph, then the relationship of friendship could represent an arrow in that directed graph. Okay, so people care about directed graphs so that they can model relationships between objects. So what I'd like to do now is I'd like to survey a few different properties one might study when one studies any directed graph. Our first notion here is a very simple one, but a very important one, called the Euler characteristic. By definition, the Euler characteristic of a directed graph G is defined with this notation, chi of G, so that's the Greek letter chi, and this is defined as simply the number of nodes minus the number of arrows. So all you do to calculate the Euler characteristic is subtract the number of arrows from the number of nodes. And this is a surprisingly interesting number. So here you're looking at a directed graph on 3 nodes and 5 arrows. So what's the Euler characteristic? Well, we're supposed to subtract the number of arrows from the number of nodes. The number of nodes here is 3. The number of arrows is 5. 3 minus 5 equals -2. So the Euler characteristic is simply subtracting the number of arrows from the number of nodes. Another thing one might care about is the so-called connected components inside of a directed graph. The most informal way that I can think of the concept of a connected component is connected components are sort of the islands inside of a directed graph. So what you're looking at here is a picture of what I consider to be one directed graph. Now, even though I'm considering this picture to be one directed graph, it's clear that there are sort of two distinct parts to it, or two islands in this directed graph. So what we would say here is that this directed graph has two connected components. Another thing one might want to do when studying a directed graph is travel from node to node via the arrows. When we do such a thing, what we create is called a path. So a path is a sequence of distinct arrows joining consecutive nodes. Here's an example to illustrate the point. Now, before I show you this example, I want to make it clear that when we take a path in a directed graph, we don't care whether or not we travel in the direction of an arrow or against the direction of an arrow. From our point of view, a path can travel with or against an arrow. So let's look at a particular path in this directed graph. The path I'm describing is described by the sequence of arrows A1, A5, A7. Well, if I'm going to go through A1 first, A1 will take me from V1 to V3. So I'm going from V1 to V3 by traveling with the arrow A1. The next arrow in this sequence representing my path is A5. Well, if I'm at V3 and I travel with the arrow A5, I'd actually be going against that arrow to end up at the node labeled V5. And then finally, the third arrow in this path is A7. If I'm currently at the node V5, I travel against A7, and then this takes me ultimately to the node V6. So if you travel from node to node, either with or against an arrow, that is considered a path in the directed graph. And there are special types of paths called cycles. A cycle is a path where the start node is the same as the end node. So here we have the same directed graph from the previous slide. I'm now declaring that the sequence of arrows A1, A4, A3, A2 describes a cycle in this directed graph. Well, the idea here is that A1 will take me from V1 to V3. Then the next arrow in this path is A4. Well, here I'm going to start at V3, so I travel against A4 to end up at V4. The next arrow is A3. Well, I'm starting at V4, and I now travel with the arrow A3 to end up at V2. And finally, the last arrow in this path is A2. If I'm at V2, I travel against A2 to end up back at V1. So we traveled with A1 against A4, with A3, and against A2. Our start node was V1 and our end node was V1. So this path is called a cycle. Another interesting property of directed graphs is the notion of circuit rank. This is probably the most sophisticated property we'll describe today. The circuit rank of a directed graph is the minimum number of arrows that must be removed if your goal was to break all of the cycles. So let's take a look at our running example here. Again, I have my directed graph on 6 nodes and 7 arrows. Now, the underlying concept of circuit rank sort of says that if I look at this directed graph, it sort of looks to me like there are sort of 2 important cycles in the directed graph. There's sort of this part over here that loops around, and there's sort of this part over here that loops around. Well, the concept of circuit rank sort of gets to the heart of the matter that we're noticing. So the question is, if my goal was to break all of the cycles in this directed graph, what is the minimum number of arrows I would have to remove in order to do this? Well, there are lots of different ways to break all of the cycles in this directed graph by removing arrows. Here's how I chose to do it. I noticed that if I removed the arrow A1 and if I removed the arrow A6, I would break my 2 cycles here, and I would be left with a directed graph that has no cycles. So I can't break all of the cycles by only removing 1 arrow, but I can remove all of the cycles by removing 2 arrows. So in this situation, we would say that the circuit rank of this directed graph is 2. So the point I'm making is that there are all of these different descriptors we can use when we're talking about the theory of digraphs. Now, another thing that might be important if we're studying directed graphs are weights on arrows. If you remember our example of financial institutions a few slides ago, the idea is that our directed graph here was meant to model financial transactions between institutions. But the issue there is that, well, every transaction carries some sort of monetary value. And we might want to know what that monetary value is in our model. So the idea of weights answers this question. You'll notice here that I've included brackets after each of the labels for the arrows with dollar amounts. These dollar amounts are called weights, and they're meant to tell us what the value of the transaction was. So remember, our first transaction, T1, represented a transaction where Wells Fargo sent Chase Bank some money. Well, now that we're using this concept of weights, we can actually see in the model what the value of the transaction was. Wells Fargo sent Chase Bank only $13. The fourth transaction, represented by T sub 4, carries a weight of 3 and points from Chase to Citi. This is telling us that in the model, the fourth transaction was Chase sending Citibank $3, so on and so forth. So we call models or directed graphs that look like this weighted digraphs. The idea is that we're attaching a number to every arrow in the directed graph. Now, we can use the concept of weights to communicate all sorts of interesting information. For example, if we wanted to, we can use the concept of weights to encode the data of a cycle. So here's an example illustrating the point. I want you to notice that this is the directed graph we've used a few times already. And what I'm doing is I'm now imposing weights on all of the arrows in order to communicate the data of a cycle. Now, you'll notice that there are only 3 numbers that I'm using as weights here. Some of my arrows have a 0 attached to them. Some of my arrows have a 1 attached to them. And some of my arrows have a -1 attached to them. The underlying idea here is that the 0s, -1s, and 1s are meant to describe whether or not in my path I traveled with an arrow, against an arrow, or ignored my arrow. The weights with 0s are the arrows that are ignored in this path. The weights are the arrows with weight 1 represent the arrows that we traveled with when we took our path. And the arrows carrying weight -1 are the arrows that we traveled against when we took our path. So let's take a look at what cycle we're representing here. A1 has a 1 attached to it, so the idea is that we're traveling with the arrow A1. A4 has a -1 attached to it. That means we traveled against A4 in this cycle. A3 has a 1 attached to it. That means we traveled with A3. And A2 has a -1 attached to it. That means we traveled against A2. The other arrows, A5, A6, A7, have 0s attached to them, which means those arrows were ignored in our cycle. So the concept of weights here is encoding the data of a particular cycle in this directed graph. And one thing I want to point out here is that negative weights are perfectly acceptable. We can use any scalar as a weight in a weighted directed graph. Now, when we have weights on our digraphs, it will sometimes be the case that we want to calculate what's called the net flow through any particular node. The notation I like to use for this is the Greek letter F. So this is called phi in Greek. And the idea is that if we apply phi to any node, this calculates net flow, which is defined as taking all of the weights in and then subtracting all of the weights out. In other words, we figure out all of the arrows that point at the node, add those weights together, then we figure out all of the arrows pointing away from the node, and then subtract all of those corresponding weights. I think this is best understood through an example. So if we go back to our financial network, the idea is that there's money flowing through all of these institutions. And when we calculate net flow, what we're doing is we're calculating the net money that moves through any particular institution. So let's calculate all three of the net flows in our example here. If I calculate the net flow through Wells Fargo, again, the idea here is we figure out all of the arrows pointing to Wells Fargo. Well, in our model, there's only one arrow pointing to Wells Fargo. That's the second transaction, T sub 2, and that carried a financial value or a weight of 9. So we start with plus 9, and then now we're supposed to subtract off all of the weights corresponding to arrows pointing directly away from Wells Fargo. Well, there's two arrows pointing away from Wells Fargo. That's the first transaction here and the third transaction. The first is 13 and the third is 137. So we subtract off the quantity 13 plus 137. And when I do all of my arithmetic here, I find that the net flow through Wells Fargo is negative 141. So the idea is that in this model, Wells Fargo is down $141 or has lost $141. If I go to Chase Bank here, Chase Bank only has one arrow pointing to it. We get a plus 13 here, but it has three arrows pointing away, and those weights are 9, 3, and 95. If I take 13 and then subtract off the quantity 9 plus 3 plus 95, what I end up with is negative 94. So in this model, Chase Bank is down $94. And if I go to Citi, I see that Citi has three arrows pointing to it, but no arrows pointing away. So all we do here is we add up the weights pointing to Citi. That would be 137 plus 3 plus 95, which is plus 235. So Citibank is the only of these three institutions in this model that is actually making money through all these transactions. Excellent. Now, remember, there's nothing wrong with negative weights. So, and everything that we've said so far is perfectly compatible with the theory of negative weights. Here's just an abstract example proving the point. In this example, I have 3 nodes and 4 arrows carrying weights. Let's say, for example, I wanted to calculate the net flow through the first node. There's only one arrow pointing at the first node. That's A2, carrying a weight of negative 7. So I start with negative 7. Then I subtract off all of the weights pointing away from the first node. Well, there's 2 arrows pointing away from the first node. That's A1 with a weight of 6 and A3 with a weight of 3. So what I'm doing here is I'm taking negative 7 and subtracting the quantity 3 plus 6. The arithmetic here gives me negative 16. So the net flow through V1 is negative 16. If I go to the second node, there are 2 arrows pointing into the second node. That's A1 and A4. Those weights are 6 and negative 9. So I start with 6 plus negative 9, which is really just 6 minus 9. Then I subtract off all of the weights pointing away from V2. There's only one arrow pointing away from V2, and that's this arrow A2, carrying a weight of negative 7. So what I do in the net flow formula is I subtract negative 7 from the quantity 6 minus 9, and the arithmetic here gives me 4. And of course, we could do our similar calculation with V3. Do that yourself and make sure that what you get is compatible with what I've written here. Okay, great. Now, so far, the only thing we've said is there's this thing called a directed graph or digraph. It consists of nodes and arrows. There are a few descriptors and things we can do with directed graphs, but we haven't said how any of this relates to the theory of matrices and vectors. Well, let's address this issue now. The punchline here is that we can use matrices to numerically encode all of the data in a directed graph. And the matrix that does this is called an incidence matrix. So if you give me a directed graph, the data in that directed graph can be represented numerically by its incidence matrix. Here is an example illustrating how incidence matrices work. I want you to notice that the directed graph that I'm dealing with here has 5 nodes and 6 arrows. So what we do is we set up a matrix and we label all of the rows in the matrix by the node labels. So I have nodes V1, V2 through V5. So in my matrix, I will label the rows V1, V2 through V5. Then we set up columns that are labeled by the arrows. So in this case, again, we have arrows A1, A2 through A6. So I'm going to be labeling my columns of this matrix A1, A2 through A6. Okay, so at the end of the day, because this directed graph has 5 nodes and 6 arrows, the incidence matrix will be a 5 by 6 matrix. 5 nodes, 6 arrows. But what numbers are we supposed to put inside the incidence matrix? Let's study this column by column. The idea is that each column is describing arrow data. The first column is labeled by A1, and it is meant to tell us what the arrow A1 does in the directed graph. Now, in the directed graph, A1 is pointing from V1 to V2. So what we do is we go entry by entry here and label each entry either with a 0, a -1, or a 1, depending on whether or not the arrow starts at the node, terminates at the node, or ignores the node. Now, so if we start at node V1, which this arrow does, we label that corresponding entry with a -1. Now, A1 terminates at the node V2, so we put a 1 in the V2 position. Because this arrow A1 ignores all of the 3 other nodes, we put zeros in those other positions. And this is how every column of the incidence matrix works. If I go to the second arrow here, the second arrow here is represented by the second column. Now the second arrow starts at V2 and terminates at V1. So we're going to put a -1 in the V2 position, a 1 in the V1 position, and then zeros in all of the other positions, because this arrow A2 ignores the other 3 nodes. If I go to the third column, this is supposed to tell me how the arrow A3 behaves. A3 points from V3 to V4, so I put a -1 in the V3 position, a 1 in the V4 position, and zeros in all of the other positions. And the idea is that I keep going column by column, building the entire incidence matrix until I've exhausted all of the arrows. So the general principle here is that each column in the incidence matrix gives information about an arrow. The source node for each arrow, that's where the arrow starts, gets tagged with a -1. The target node, that's where the arrow points, gets tagged with a 1. And all of the other nodes get tagged with zeros. So we build the incidence matrix column by column to represent all of the arrow data. Now, the point here is that humans like pictures that look like directed graphs, but computers like numerical data, which is represented by the incidence matrix. But the beauty of this theory is that there is nothing lost in this translation process. If you give me the incidence matrix, I can reconstruct the picture of the directed graph. So here I have an example where someone has given me the incidence matrix of a directed graph, but I don't have a picture of the directed graph. That's totally fine because I can use this incidence matrix to reconstruct the picture of the directed graph. The first thing to note here is that my incidence matrix here has 3 rows labeled by V1, V2, V3. What that means is that the directed graph I'm studying will have 3 nodes, V1, V2, V3. So now all we need to do is go column by column and figure out how all of our arrows point between these nodes. Notice that this incidence matrix has 4 columns, which means ultimately this directed graph will have 4 arrows. If we look at the first arrow labeled by A1 here, notice that we have a -1 in the V1 position, a 1 in the V2 position, and a 0 in the V3 position. What this means is that our first arrow starts at V1 and points to V2. So our first arrow starts at V1 and points at V2 and ignores V3. If I go to our second column here, this will tell us how our second arrow starts and finishes. I have a -1 in the V1 position, a 1 in the V3 position, and a 0 in the V2 position. This means that my second arrow starts at V1 and points to V3. What about the third arrow? If I read this third column, it's telling me that my third arrow starts at V2 and points to V3. And my fourth column is telling me that my fourth arrow starts at V2 and points to V1. I've exhausted all of the columns here. I'm left with a picture of my directed graph on 3 nodes and 4 arrows. So if you only give me the incidence matrix, that's all the information I need to reconstruct the full picture of the directed graph. And now the interesting thing about matrix theory is that interesting properties that we might consider geometric when it comes to studying the directed graph can often translate into algebraic properties of the incidence matrix. This is what would allow a computer to run algorithms on a directed graph. Now, here's something I'd like to point out. In general, if your directed graph has m nodes with n arrows, the incidence matrix will look something like this. Remember, all of the rows are labeled with the node labels, and all of the columns are labeled with column labels. So with m nodes and n arrows, your incidence matrix will be an m by n matrix. Now, what if we're studying a weighted directed graph? Well, a weighted directed graph is the data of a directed graph with extra data on top of it, and that's the data of the weights. So the directed graph itself is represented by the incidence matrix, but the data of the weights ends up being stored inside of a separate vector. We call that vector the weight vector. So here I have an example where I'm studying a weighted directed graph on 3 nodes, and it looks like 4 arrows. Each of my arrows is equipped with some weight. If I want to store this information, it turns out that the proper way to do it is to stick it inside of a separate vector. We call this the weight vector W. And so the idea is that there are 4 positions inside of the weight vector, and each of these positions is meant to tell us which arrow is tagged with which weight. So again, in this situation, my first arrow has weight -3, so -3 is the first coordinate of my weight vector. My second position in the weight vector tells me what the weight is for my second arrow, and that's equal to 7 here. The third coordinate of the weight vector is telling me what the weight for the third arrow is, that's 14. And the fourth coordinate of the weight vector is telling me the weight for the fourth arrow, which equals 9. So we're storing the data of the weights of the 4 arrows of this particular directed graph inside of a weight vector in r to the 4. So again, because there are 4 arrows, the weight vector belongs to R4. Now remember, we can encode the data of a path with weights. And when we do this, we call that weight vector a path vector. So here, what I'm looking at is a directed graph where I've used the concept of weights to encode the data of a particular path. The idea here is that the path I'm taking, remember, I'm using weights 0, 1, or -1, depending on whether or not my path ignored my arrow, whether or not the path went against an arrow, or whether or not the path went with an arrow. For this particular path, note that A3 is carrying a -1. That means in the path we went against A3. Notice that A4 is carrying a 1, which means the next thing we did was we traveled with A4. Then notice that A1 is carrying a 1, which means we traveled with A1. This path ignored the arrow A2, so A2 is equipped with a 0 in this description of our path. So if I encode those weights into my weight vector, what we do is we call this the path vector. A1 has a 1, so the first coordinate is 1, the second coordinate is 0, the third -1, and the fourth 1 in this situation. And of course, if our path is a cycle, we would call this the cycle vector. So here, let's say that I took a cycle in this particular directed graph. Let's say that I jumped from V1 to V3 by going with A2. Then let's say that I went from V3 to V2 by going against A3. And then let's say that I went from V2 back to V1 by going with the arrow A1. If that is my particular cycle, I can use the concept of weights to numerically encode this cycle. The weight vector here would be telling us whether or not in our cycle we went with an arrow, against an arrow, or ignored the arrow. Well, in this particular cycle, note that we ignored A4. We didn't use that in our cycle. So the fourth coordinate gets a 0. In our cycle, we went with A2. So the second position gets a 1. And then we went against A3 and against A1. So the third and first coordinates get tagged with -1s. So the cycle vector of this particular cycle is the vector -1, 1, -1, 0. Okay, so if we take survey of this theory of weighted directed graphs from the perspective of linear algebra, the idea is that we start with the data of a directed graph on m nodes and n arrows. So that means my incidence matrix is an m by n matrix. Furthermore, if I have weights on my directed graph, the data of the weights is encoded in a vector in r to the n. And if I stare at this situation for a moment, I realize that there's something interesting that might happen. Here, my matrix is m by n, and if I'm thinking in terms of matrix vector products, I might use the arrow notation to communicate this. Since A is m by n, I can view it as a machine that can be multiplied by vectors coming from r to the n to produce vectors in r to the m. And lo and behold, the weight vector is precisely a vector in r to the n. So I'm allowed to multiply the incidence matrix by the weight vector always. So the product A times W when I'm dealing with weighted directed graphs makes sense. Here, again, A is the incidence matrix and W is the weight vector. So let's look at an example where we do this. Here on the left, I have a weighted directed graph. Remember, the directed graph itself is just the nodes and the arrows, and that data is encoded in my incidence matrix. For example, the third column here has a -1 in the second position because my third arrow points from V2, and then it has a 1 in the third position because it points to the node V3. But on top of the directed graph, I also have the data of the weights on the arrows. The weights here are -3, 7, 14, and 9. So those are the coordinates of my weight vector. Well, in this situation, my incidence matrix is 3 by 4, and my weight vector is a vector in R4. So I'm allowed to multiply my incidence matrix by my weight vector. And what happens when I do this? It's worth asking. Well, what happens when I do this is I produce the vector 5, -26, 21. So what am I doing? I'm multiplying A by W, and I'm producing a vector in R3. Well, what is relevant about 3 in this particular situation? 3 is exactly the number of nodes in the directed graph. And if I look at the first node in this situation, well, maybe for the first node, I might want to calculate the net flow. The net flow adds up all of the weights pointing to that node and then subtracts off all of the weights pointing away. Well, there's only one weight pointing to V1, that's 9, and my two weights pointing away from V1 are 7 and -3. Well, if I took 9 and then subtracted 7 and then subtracted -3, that would get me the number 5. That's actually the net flow through the first node. And if I calculate net flow on the second two nodes, I would get -26 and 21. So what happened here when I multiplied my incidence matrix by my weight vector? I produced my vector of net flows. The first coordinate of the matrix vector product is the first net flow. The second coordinate of the matrix vector product is the second net flow. And the third coordinate of this matrix vector product is the third net flow. So by separating out the numerical data of the directed graph and storing it inside of the incidence matrix, And by separating out the data of the weights in its own vector, I can apply the concept of matrix vector products to calculate all of the net flows all at once. So I don't view these as three separate calculations anymore. I view it as a single calculation. So we can summarize this with a theorem. In any situation where you're studying a weighted directed graph, if you have m nodes and n arrows, your incidence matrix will be m by n, which in arrow notation is communicated as A goes from Rn to Rm, and your weight vector has exactly one scalar per arrow, which means it is a vector in R to the n. So not only are you always allowed to multiply A by the weight vector, but there's meaning to doing that. The ith coordinate of that matrix vector product always gives you the net flow through the ith node. So this is a pretty cool application of the concept of matrix vector products. On one hand, you can view A here, the incidence matrix, as just a simple grid of numbers meant to store data. That's the data of the directed graph. But you can also view A as a process via matrix vector multiplication. Multiply your incidence matrix by your weight vector, and you produce all of the net flows. So that's a really cool application in my opinion. I just want to quickly direct your attention to the Sage calculator that I've included for this lesson. Let me make this a little bit bigger. So one cool thing about Sage is that it's sophisticated enough to work with directed graphs. So I've kind of included a sort of tutorial here where I've done the coding for you. And so here what I've done is I've reconstructed the picture of this directed graph using the syntax of Sage. If you click evaluate in my pre-written code here, what you'll do is you'll produce a picture of the directed graph that's embedded in Sage. Even though this picture might look different to the untrained eye, if you look closely, you'll realize that this has exactly the same structure as the original picture I have above here. And of course, I've also included the syntax here for producing the incidence matrix of a directed graph that's on this fifth line of the code. If you click evaluate, this will give you the incidence matrix. And if you want to, you could equip your directed graph with weights on the arrows. And if you store those weights inside of a weight vector, you can then do the matrix vector product to calculate the net flows. So if you click evaluate, that will happen here. So take a look at that and play around with it and see if it helps you on your homework. Be careful, Sage imposes an ordering of the arrows, which means it imposes an ordering on the columns. So if you're working with a directed graph and you're trying to use this, just make sure that the incidence matrix is exactly the same as yours. Otherwise, you might need to relabel your arrows to align with the way Sage did it. So that's all I got on directed graph.